Hello, this is Patrick O'Shaughnessy. I'm a certified industrial hygienist and professor at the University of Iowa, and I will be discussing methods to compare real-time data obtained in two work sites in this module devoted to data capturing and organization, and it's associated with this InTERACCT series. The learning objective for this module is to allow you to be able to compare concentrations measured at different sites within a workplace using real-time data. So I would like to provide some information on direct comparisons between sites using DRI data that you've obtained at more than one site, and therefore it would make sense that you would want to try to compare between them. This analysis will involve the use of a t-test, or at least allusion to it, and if you are unfamiliar with that statistical technique, then please view the statistical analysis modules in which it is fully explained. Here are plots of both Station 1 and Station 2 described in the previous part of this module. And recall that Station 1 has a mean of 148 parts per million. Looking at Station 2, it could be said that it has a different sequence over time, but that the average trend is relatively similar to that of Station 1. And from the descriptive statistics, it has a slightly lower average of 126 parts per million. And in Station 2 data, there also appears to be what I would consider a periodicity to the data. So there seems to be some cyclic nature that's developing that's causing spikes within it at more or less regular intervals. So there may be a story right there. Why is that happening? What's going on within the plant to create that data pattern? And these are questions that the use of a DRI can help to answer. A simple way to compare between the two stations is to perform a visual comparison as shown here, in which data from both stations are plotted together. You can now see that they overlap each other quite a bit, and you might conclude that the concentrations are close enough together that there isn't enough difference to be concerned with. However, it may be worth exploring from a statistical standpoint as well. The way to make a statistical comparison between two samples is to apply a t-test comparison. And for that we use the data analysis function called t-test two-sample assuming unequal variances, because typically you would assume unequal variances between your two samples. Again, this will be explained in the next module on statistical analyses. The output shows that the means are 147.9 and 125.9. But the rest of the output is a little confusing in Excel. In essence, the comparison is whether or not they are different, not whether one is bigger or smaller. So that's what's referred to as a two-tailed test. And the p-value given for the two-tailed test is 1.8 times 10 to the minus 14, which is extremely small and way lower than the typically applied what they call alpha value of 0.05, which indicates at least 95% confidence that they are different. Therefore, by this t-test, yes, the means of the two data sets are significantly different, meaning that the data values derive from two distinct populations of concentrations. However, there are complications with the use of a t-test derived from a direct reading instruments. First and foremost, the data are not randomly sampled from the atmosphere. You are not going out and grabbing one sample and then recording it, and then going out again and taking another sample and recording it, etc. A DRI is taking sequential, minute-by-minute samples, in which case you wouldn't expect the concentration to randomly flip from one side of the mean to another. But that's what happens in a random sample, because you have an equal opportunity of taking something a little bit higher than the average or a little lower than the average with every sample. When you are randomly sampling, each sample is also independent from one another. However, that's not true for DRI data. The association between one data value and its previously recorded data value is referred to as being autocorrelated. This occurs in situations that do not change drastically between each sample because the sample period is so close to one another. So one data value of concentration is not much different from the next one. High concentrations correlate well with the next value, which is also high, etc. The consequence of this is that when the data are autocorrelated, it greatly increases the possibility of producing t-test results that demonstrate significant differences between sites, which is called inflating the alpha error. The test says they are different when they are not. For example, one way to look at autocorrelation is to plot the data values versus their most previous value, which is easy to do in Excel. As you can see in this plot, using the Station 1 data, they line up pretty well with a correlation of 0.91. So these are what would be considered highly correlated, and therefore also not independent and random relative to the mean. To better understand what randomly measured values would potentially look like on a plot, the time series shown here was generated with a random number generator to have a mean of 148 and a standard deviation of 27 parts per million and be normally distributed about the mean value. So as mentioned, they would plot randomly above and below, as you can see here. The correlation plot of data values versus their most previous data value, in this case, as you can see, shows no trend at all, so there's absolutely no correlation. But this scenario does not typically happen when you are taking DRI samples of an aerosol or gases and atmospheres, again because the sample rate is much higher than concentrations will change randomly over time. Therefore, given the presence of autocorrelation and the lack of independence of the measurements, don't apply a t-test. It will always show significant differences because of that autocorrelation and because of the very high sample size that drives the test towards a significant difference between them. It's almost a guarantee that they will be different. Again, with over 100 data points in this case and autocorrelation, a statistical difference will be found even though the averages of the data values are very close to each other. So it's an exercise with a known outcome and therefore essentially worthless to make without proper accounting for the autocorrelation, which is possible, but a statistical undertaking beyond Excel's capabilities. Therefore, the best practice is to go back to descriptive statistics and graphical displays of the data, then use your common sense, or what they call your expert judgment, when making comparisons to answer questions such as, what are the average concentrations? Which data sets have extremes that I'm concerned about? Are the data sets different enough to have a concern of one relative to the other? So in the case of Station 1 versus Station 2, probably not. And so then you may be looking more at the specifics of, say, the nature of the sample site that might be worth investigating rather than concerning yourself over statistical differences between the two sites. To end this second part of the data capturing and organization module, an alternative to trend analysis for comparing two or more measured areas is to create a box plot. As shown in the graphic, a box plot splits up the distribution of data collected vertically by showing a box that contains 50% of all the data from the 25% quartile at the bottom up to the 75% quartile at the top. You can see the mean and median are also shown within the box, as well as the extent to which the distribution of data values extends and includes values that are far out on the tail if they exist, which are called outliers. So this graph was developed using the box plot graphing option in Excel. And as a tip, as shown on the far right, it's best to organize all the values from Site 1 on top of those from Site 2, and then highlight them all in the box plot function as Station 1, Station 2 are all the X values, and all the numbers are just the one set of Y values. So there's just one series associated with it. And that will separate them by notation given in the first column, which results in the nicely spaced boxes within the graph, as shown here. In this case, you can see that Station 1 has a slightly higher average than Station 2, but you can see that the distribution of the two are fairly similar, and there's a lot of overlap between them, which may be the main point to get across. And with that, I'll conclude this module.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program. a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.